Well, it's 6 p.m. Eastern Standard Time. This is the Randomizer. I'm Charles Schultz, your host, and we're going to be talking about some very interesting things tonight. Let me get my information up here. First of all, I encourage you to go to schultzlaboratories.com, register and become a member of our Universe Science Center, and also to join our weekly Monday night chats and lessons this week on the 31st, Monday, at 9 p.m. Eastern Standard Time. We begin our six-part lesson on, well, of all things, meta world. We're going to talk about the advancement of humanity from sticks, fire, and rocks all the way up to nanotechnology and where we appear to be headed. So this is our chat about the future, how we're developing, and why. And we're also going to cover some very interesting things along the way, such as our realization of the limits of uncontrolled industrial growth and how it's affecting our world and what we can do about it. So this is going to be a very interesting look into not just our development of technology, but how human beings think about technology and where it could be leading us. So Meta World, every Monday night at 9 p.m. is live. Go to the Schultz Laboratories site and go to the Universe Science Center site. Both of those sites will lead you to the page that allows you to register for the course. And it's 6 classes, 1 hour each time with a discussion period at the end. So be sure to join us. It's a lot of fun. And we've had a lot of participants, and they really enjoyed our last class about SETI. So tonight, our randomly selected term, we have a program I've written that has about 1,600 terms and words in it, and we throw the dice every day and get a new one, and tonight the word is quasiperiodic. Now everybody knows what periodic means, which is happening on a regular basis, something that happens at an interval that's easily predictable. And one of the things that you can easily see would be the ticking of a clock, or if you're tiling a floor, the tiles fit together in a regular and repeating manner. So that's a periodic operation. So what's quasi-periodic? Well, it's kind of interesting. In some cases, when you go to examine a system or learn about the system, you'll find that it isn't exactly predictable, that there's some small element of chaos. Think of it as a handful of hot sauce or broken glass thrown into the pattern. And it means that no matter how hard you try, you can't quite predict the exact structure. You can mostly predict it. Good examples would be the weather, for example. We are quite adept at analyzing changes in temperature, movement of wind and moisture, and how it will condense and when it will rain. And it seems that we used to be better at predicting the weather in the past than we are today. Weather is not 100% predictable, but it's mostly predictable. And the most periodic element of the weather is, of course, the rising and setting of the sun. So you would think that with a regular cycle of sunrise and sunset, temperatures going up and temperatures going down, that overall the weather would be a very simple pattern. But it isn't, because other complications arise. And one of those complications is the introduction of moisture. If you think about it, water itself doesn't seem to be too terribly influential, although when we look at the effects it has on erosion and changes in the planet, it is. So the quasi-periodic element arises when we see that water can change form. Now you can imagine the rain falling on an area and wetting the ground, and for a while it will change the way heat is taken up or released in the environment. But what happens when the temperature gets cold enough that the water freezes? Well, a very interesting thing begins to happen. You normally could predict from the incoming sunlight how the temperature would rise. But when the ice forms, when the snow falls, because of the fact that it is white and it reflects heat, it actually drives the temperature down further. So water has a non-linear effect on the weather. And there are other reasons it does as well. So where we normally could predict how the temperature will rise and fall with the rising and setting of the sun during the course of a day, when you get to the point where there's a change of state in the water, it throws the whole curve out of whack. And this can even be seen just in rainfall patterns, because clouds themselves will reflect sunlight and cause the temperatures to drop a little. So quasiperiodic effects are those that have a strong element of order at their heart, but then some element within them is random and unpredictable. So anybody who can think of examples of quasi-periodic behavior has questions about it. We're going to get to that in just a few minutes. I encourage you to ask questions and make comments. Now, I'm going to introduce something that came from a mathematician by the name of Roger Penrose. If we tile a floor, we know that we can tile the floor in a very regular manner with triangles, for instance. Equilateral triangles will fit on the floor very nicely, and they'll cover the floor entirely with no gaps or overlap. So it's a perfect tiling. We can do the same thing with square tiles or rectangular tiles if they're the same dimension. We can also use hexagons, regular hexagons, and tile a floor, and it will do so exactly. It will do it without overlap and without gaps. Now, if we think about it, triangles with 3 sides, squares or rectangles with 4, hexagons with 6, will all tile the floor pattern absolutely uniformly without any issues. What about a pentagon? Well, you see, that was a big problem for a long time, and pentagons will not fit together without creating a gap. Now, you can see if you did the same thing with octagon, the stop sign shape. If you fit the octagons together perfectly, just as you would normally expect, you will have regular square-sized gaps at the corners, and this is actually a pretty popular floor tile. This is a periodic tiling, but with 2 shapes. And it isn't as pure, you might say, as just hexagons or squares or triangles, but it is an actual periodic tiling. What happens if you try to do it with pentagons? You get gaps, and the pentagons will not fill the gaps. This is where the mathematician Roger Penrose steps in, a very brilliant guy, and he was actually in charge of the mathematics department of a very major university for a number of years. He wrote a number of books on the subject, and he took this question to heart. Could I create a tiling that would exactly cover the plane with no gaps, but based on the pentagon? Well, he thought about it a lot, and he came up with a very interesting solution. He broke the pentagons into 2 different shapes, what he called darts and kites, based on their shape. So the kites were kind of diamond-shaped, and the darts were narrower, almost needle-shaped. They had 2 different basic angles. And by using darts and kites, he was able to construct the pentagonal form and tile the plane. But here's the catch. The tiling that he created was not a regular tiling. It was not completely periodic. Because of the nature of the way the tiling worked, he ended up having to add what looks like a little bit of chaos into it. It created a quasi-periodic tiling. It does indeed completely tile the surface. Well, because of the fact that it isn't exact or it isn't perfect, you will find that when you start tiling, you'll reach a point where the tiles won't fit. You can't make another pentagon and fill it, which is to be expected. So you have to do a few tricks where one of the opposite tiles fills in the gap, and then you can continue with this little bit of chaos, but it still perfectly fits. Quasi-periodic tilings are actually quite common in nature. When we take a crystal of metal and we shoot a beam of X-rays through it, the X-rays will go through it something like a lens, but more like going through rippled glass, and it will produce a regular pattern of dots or lines so that you can look at it and say, that's a hexagonal pattern or a cubic pattern. And it's easy to identify because of where the X-rays focus. Quasi-periodic tilings will give you bright and dark spots in the pattern so that you can see that it isn't entirely regular. And this occurs a lot in minerals. Specific minerals do have some element of 5-fold rotation in them, but with a bit of randomness thrown in to make it fit. And this is very important. We'll get to this in just a moment about the importance of the irregular nature. When you start looking at the regular portion of the structure, you can see strong elements of crystal nature in them. When you get to the non-periodic elements, you're wondering, well, what would make that happen? In the case of many metals, it's because there are impurities other metal atoms in there. And many people don't think about this, but atoms come in different sizes. So sometimes the size of the atom will be such that it creates a strange bend or a pucker in the crystal in order to make the fit of that particular atom correct. And so quasiperiodic tilings can occur in metals. Now, recently, people who were messing around with specific very pure elements and combining them in odd ways discovered something they call quasicrystals. Quasicrystals are not naturally formed in most any circumstance, although tiny samples of them have been found in exotic conditions. Quasicrystals are like the new Teflon. Because of the way it's bound, it tends to be an extremely stable chemical compound, and it's used to coat griddles and frying pans and defense hardware with a coating that is very tough and doesn't wear off. As you know, Teflon is pretty good at not sticking to anything, except that label they put on it, somehow it sticks. Figure that one out. But Teflon isn't very tough, and it tends to scrape off fairly readily. Quasicrystals, on the other hand, can be extremely hard and durable, and can be used to coat a lot of different objects quite successfully. So there are examples in nature of quasi-periodic things. Now let's look at another thing. This is a big one. People, as I mentioned, try to predict the weather on a regular basis, and they also try to predict larger trends in our climate. It's not going to happen, and here's the problem. There are many different cycles that happen in the movement of our planet in its orbit, and in the tilt of the axis of our planet. It's like a spinning top running down. And if you ever played with a top as a child, you spin the top and it's upright. And after a while, it starts to wobble. And this is called precession. And as it wobbles, the pole doesn't point in one direction. The axis is moving and describing a circle that's moving around. And sometimes there's a smaller wobble on top of it. Our planet wobbles in exactly this manner. In fact, every planet rotating does. Mars, for example, rotates pretty wildly and goes through some very, major shifts in the inclination of the planet. And this has a great effect on its climate, how hot or how cold it is. If the planet is perfectly vertical, ice gathers at the poles and the climate gets cold very quickly. And on that planet, the atmosphere actually starts to freeze out and snow out. When the planet tips down to a much higher inclination, the poles get heated long enough during each half of the year, summer and winter, to allow that material to melt or evaporate or sublimate, become a gas again. And then the planet goes through wild climate swings. The Earth does this also. But we have a stabilizing factor. You can think of it as a ballast stone, and that is the moon. The fact that the moon is orbiting our Earth in a regular manner, it actually acts as a ballast to keep the balance of our pole from shifting very much. So our climate is much more mild. The changes are not as radical as they would be otherwise. So we can thank the moon for that. But here's the issue. Because of the length of time that our planet's pole does go through these gyrations, it causes cycles of many thousands of years in the changes of our planet's climate. Ice ages occur every 11,700 years approximately, and we are actually due for one right about now. And we will notice that our climate appears to be getting a little wild. Well, here's the issue. We've actually been in a period of time where the climate has been very mild. For the last 5,000 or 6,000 years, it's actually been stable enough for us to reach the technical pinnacle that we are achieving today. With huge disastrous changes in weather and local climate, what will happen is it'll set civilizations back. We need quiet, peaceful times without a lot of destructive influence in order to reach our full potential. And we've been able to do that. But now we're seeing changes in the cycles. And small ones have happened in the past, and we know about this. I mean, think about this. Greenland was not named Greenland as a joke. It actually was green at that time in many of its areas. And Iceland isn't covered with ice. It actually has a cyclic pattern throughout its year, and it has some very beautiful verdant spaces. So actually, these were not named as a joke, as I mentioned. They were named that way because that's what people saw. So these changes are regular. We see them all the time. Our weather is not predictable because it is quasi-periodic. There is that element of randomness that no matter how hard we try, subtle, creeps in and overwhelms what our normal calculating selves would imagine to be the proper answer. So, at this point, I'm going to open up for anybody with questions or suggestions on the concept of being quasi-periodic. And I welcome Donna to the chat. Thank you for joining us. I think it's really interesting because there are actually very simple mathematical equations, one called the strange attractor, which shows the quasi-periodic behavior and then leads to something known as fractals. So imagine an equation that you put a number in and you perform the function and you get an answer. What happens if you take the answer and put it back into the equation again? Now this iterative equation where you put in a starting point and it spits out an answer and it goes back in and it spits out an answer and it goes back in and spits it out. If you plot it on a graph, you will get numbers going up and down in a certain way. And eventually, the numbers will converge on an answer and settle there. What's interesting about this is that an exceptionally tiny beginning change, a start to the beginning value, can have wildly different results when you start graphing it. So, a quasi-periodic system is very much like this. It is literally bound chaos. With many of the strange attractor equations, you'll find that if you put in random numbers to start with and you run it enough of the times, they'll split onto 2, 3, or 4 levels, and eventually you'll have these 4 straight lines coming out of the graph where the value has settled. Now, this is related to the fractals, where you see these amazing deep descent geometric repeating patterns. It's the same sort of a structure, and fractals are calculated in exactly the same way. Fractals are quasi-periodic. You will see the same structures like the leaves of a fern, and you magnify it 1,000,000 times and there's the same structure in there again. Biology does actually take advantage of quasi-periodic features, and the fern leaf is a very good example of that. And the way it works is, believe it or not, the chemistry involved in telling a cell what to grow and what its destiny will be performs a computation. Our cells are literally computing machines based on chemistry and physics. So as the cell is operating, it is calculating the next result. And the next result sometimes reaches a threshold and sticks there. This happens in our climate from time to time, and that's when the ice ages begin, and also when they end. So when certain non-periodic elements begin to overwhelm the periodic results you would expect, the system will change state. Now, the use of the term system is what's important here. When we deal with simple things like a box full of ball bearings, there's an absolute geometric way they will pack the best. When we look at a machine that produces stamped out metal parts or chocolate chip cookies or whatever on an automation line, we find that there is a critical set of numbers that produce the best result all the time. We're striving for a specific solution. When it is violated, the machine malfunctions and this line shuts down because you got to get back on track. We're just beginning to reach the understanding of the complexity of systems. In a system, many parts work together to produce the result. Quasi-periodic behavior in a system is one of the things that gives it definite states that it will achieve and stay in as if it's in a rut. And this is not stability, but meta-stability. So a meta-stable system is one that settles in a way of behavior, but a push in the wrong direction or the right direction will cause it to fall over to another state. So imagine a rectangular box standing on end, and it may balance there, but it doesn't take much to push the box and have it tip over and fall into a new, more stable configuration. So quasi-periodic operation in a system can cause this to happen. And our climate, again, is just one such example. Another would be the movement of the Gulf Stream. Warm water from equatorial or Caribbean areas of the Earth has formed a flow, a stream that travels up into the northern areas where England is located, the United Kingdom. And that warmth actually makes that island 10 to 20 degrees warmer than it would be otherwise. It is the arrival of that warm water that sets the climate in that area. Now, why is this important? Well, without that flow of warm water, the climate in that area would shift drastically and it would be icy, extremely cold, and possibly far less habitable than it is today. What's important here is that the factors that created that Gulf Stream, that warm flow of water, and there are other similar flows of water in our oceans, those factors can be tipped in the wrong direction and that flow can be disrupted. We don't even know what it would take to change or disrupt that flow. It is in our best interest in many cases to maintain that flow because the damage to local populations, their industry, and their ability to produce food could be catastrophic. It is only when we understand the operations of whole systems that we're able to even begin to have an element of control exerted over them. One of the things we're trying to do as a growing civilization, a technical civilization, is to reach a stage where we can properly manage the environment of our planet so that we can prevent major catastrophes or disasters from occurring. Many of them would be things like cyclones or monsoons or typhoons, hurricanes. Basically different words for the same effect, very dangerous weather. If we could reach that stage of control, we might even learn how to control volcanic activity or earthquakes to find a way to tip their actions into a lesser dangerous, more controlled circumstance or to eliminate them altogether. And I don't think that's going to be very easy because the compounded forces of magma moving under the crust create expansion and contraction and movement, the sliding of plates. I think that's something for a real super civilization to learn to control. But it doesn't mean it's out of our grasp. It simply means it's a system we don't have the capacity of understanding just yet. So, quasi-periodic, mostly orderly with a dash of disorder put in just for flavor. Penrose tiles, as I mentioned, are an interesting example. And for that, I have to go back one more step. Even though Roger Penrose is credited with the development of the pentagonal Penrose tile set, it was discovered a few years later that some of the ancient mosaics found in Morocco actually showed the pentagonal Penrose tile set. So it turns out to actually be a solution that's thousands of years old. It begs the question if he was aware of it previously. But it is an interesting result, and it took a lot of thinking to reach it. For a long time, it was thought to be unreal, unreachable, and he did in fact present a solution. And then later, the discovery of quasicrystals, which can form perfect dodecahedrons, 12-sided pentagonal ball structures. Those are pretty amazing, and some have actually been found in meteorites. You're not going to find them just laying around anywhere, however. It generally takes materials like samarium and lutetium and a couple of other oddball elements crammed together under just the right conditions and then grow them in a vacuum or something. So quasicrystals are weird and unusual things, but they do exist. They have been shown to exist, and we know how to produce them on a regular basis now. So if we have any questions, please bring them forward. Otherwise, I'm going to plug our service. Hello, Donna. Please ask a question if you will.
Well, it may not even be relevant, but are there any quasi-periodic systems in the human body?
That's an interesting question. I know that years ago, there was an analysis system that people came out with based on synchronicity. It was the change of the intellectual cycle over so many days and some physical cycle. There were 3 different cycles that they put together and calculated when they overlapped a certain way. I don't know how technical or scientific it was. It seemed to me kind of a new agey thing. But that would have been a quasi-periodic system to a degree. You had three different frequencies of event that overlapped, and sometimes they would cancel each other out, and sometimes they would add up to a drastic swing in behavior theoretically. I think that that's probably the closest that I would know of. On the other hand, I would like to point out that biology regularly creates five-fold rotational symmetry, and you can see that in five-armed starfish or echinoderms like the sand dollar or the sea urchin. They have a five-fold rotational symmetry, as do crinoids and other feather stars. So nature has made that sort of a pattern appear, the five-fold rotational pattern, but it does so by controlling the structures of proteins and how they fit together, and then eventually the cells that make the larger macro structures. Um, so we do have a number of examples of quasi-periodic activity and materials in nature. And I hope that's a reasonable answer.
Yes, thank you. I have one more.
Okay.
A term that I came across while looking this up was pseudo-periodic.
Ah, yes. Okay. Pseudo-periodic is an operation or a process that appears to be periodic but actually is not. It can fool you. I can give you a good example of that. You can imagine tiling the floor with, say, 3-inch tiles, square tiles, and then throwing in some 3 by 6 tiles, oblong ones. Well, you could do that in a regular way, or you could scramble them up. And no matter what you do, you're going to be able to fill all the holes or gaps with either the long tile or the square tile. What's interesting about this is you could tile it in a regular manner in a number of different ways, or every now and then, just for the heck of it, you could throw in some randomness and it would still fit together. And the pseudo-periodic portion of it is this. All of the corners of those tiles will always fit on exactly unit or 2-unit distances. So if you were to have atoms that did that and you shot x-rays through it, you would see this square matrix with some elements of rectangular shadows in it. That is a pseudo-periodic operation. So we do have those things in nature, and we also do have them on some sloppy non-OCD floor tilers results. So I've seen them myself. Well, at this point, I'm going to say that we have a number of books and publications on our site that are available for sale. We also have memberships for Schultz Laboratories and the Universe Science Center, and for our upcoming class, Meta World. We encourage you to join us and help us grow and add more diverse interactive 3D environments and exhibits, and to see our publications and our podcasts and join our classes. They're a lot of fun, and you're sure to learn something you never thought of. So schultzlaboratories.com and universesciencecenter.com. And again, our word today was quasi-periodic, and I encourage you to look it up as you did. I encourage everyone to look that up and to also look up pseudo-periodic, because yes, they're closely related terms. Look up Penrose tiles if you want to have some fun. I imagine a few people might end up putting them on their floor at some point. They can drive you nuts. A lot of fun to do. And I've had some fun playing with them myself. Well, I'm Charles Schultz, and I hope you've enjoyed tonight's Randomizer chat. Tune in tomorrow at 6 p.m. Eastern Standard Time for the next one. We'll pick our new term then. And thank you for everyone for participating and making all of this possible. Everybody have a wonderful night. Take care and make the world a better place. That's my best piece of advice. Thank you for tonight.